That's pretty fascinating. Maybe they're trying to be like Warren Buffett. He like famously had billions of dollars and lived really modestly. Okay, elevator. Who knows the answer to this question? If you're at rest in an elevator, but then you start accelerating upward, how do you feel? We're going to talk about our feelings today. Oh, man. That's what I live for. Talking about our feelings. Right, Julia?
I feel a little nauseous.
So here's you. Here's you. You're in an elevator, and the acceleration vector is pointing up. So what direction is the net force? Up. Okay. So then how would you feel then? Would you feel heavy, or would you feel light, or would you feel the same? You feel heavy. Yep. So your force diagram, here's you. So you gotta make sure when you draw your force diagram, like this is you. You have a mass of M. It's you. Okay. So there is, I shouldn't draw an arrow. Arrows are now very particular things. Anyway, that's you. There's gravity pulling you down, mg. And there's the force from the elevator floor pushing you up. Now this vector is bigger than that vector because you need the net force to push you up, to accelerate you upward. So then, this of course raises I feel like I've asked you this before, maybe not. What makes you feel like your weight? Incorrect. You've fallen for my trap.
Is it acceleration normal force?
Yes. Well, it's actually there. Yeah. So if you say gravity, I would say this to you, right? Last time you jumped out of an airplane, how did that feel?
A little scary.
So here's something. Let's say here's you in an elevator. Here's a thought experiment. You might have not thought about this before. If we'll cut the cable. And now you're just falling. You're in free fall. You're free falling. Okay. How do you feel when you're free falling? You'd feel weightless. Okay. If you've never considered that before, then something for you to think about, I guess. If you're bored today, if you're falling, you would not feel any weight. You'd feel like an astronaut out in 0G, right? But wait a second, when you're in free fall, aren't you still experiencing that mg? So therefore, it has nothing. Your weight. I shouldn't say it has nothing to do with gravity. It's involved, but it's not gravity because obviously, when you're experiencing the force of gravity, you can feel weightless. So what really is making you feel that weight is the fact that the ground. So when you're standing here, there's mg pushing you down, and there's the normal force from the ground. Normal from the ground. This is really what makes you feel that sensation of weight, is the ground pushing on you. Yes?
Isn't also like in the elevator there why you feel weightless is because it's confined and there's like no air resistance?
Well, I mean, let's just send you out of the plane.
Like because
Yeah, if you're falling in air, so you're surrounded by air molecules, you're still going to feel pretty much weightless because mg is pulling you down. And there's going to be some air resistance, right? Like those force diagrams we drew at the beginning. So I wouldn't say that's going to be the same, because if you think about the sensation of weight is very peculiar. The floor is pushing on my feet while gravity is pulling all elements of my body down. And so your body's actually kind of compressed in this kind of funny way where holistically you experience that as the sensation of weight. That's like, okay. And you got all these nerves and like your ear fluid and all that stuff for balance. You guys know what I'm talking about? Yeah. So all together, if you've ever lost your sense of balance because of like illness or something, you would know like, whoa, like it doesn't take much for you to be like, oh, this doesn't feel normal. So anyway, here's another thought experiment for you. All right, I put you in an elevator box, but it's out in outer space. We're in space. Ooh, spooky. We're in deep outer space. And here's a little rocket booster. Okay, here. Oh, that's cute. It's like a little rocket ship. Now I put you in there. So you're in deep outer space. How do you feel if it's just chilling? You're floating, you're weightless. Could we make you feel a sensation of gravity? Yeah. What if we just have this thing accelerate at 9.8 meters per second squared? Well, think about what's going to happen. F net equals ma. So the net force, if you're accelerating this much in your rocket, because here's your rocket booster, right? Then your net force must be m times 9.8. And what direction is that force? Well, it's pushing on your feet, isn't it? So if I put you, it would be exactly the same. You would have, this is actually a famous, this idea is part of what inspired Einstein to come up with this whole theory of relativity, was this thought experiment of, is there really any difference between being in a box accelerating through space and being on a planet with gravity? Is there really any difference? And he was like, nah. There's a whole thing in physics about, we won't get deep into this, but like about how this inertial mass, meaning the mass, in this formula is the same mass that gravity sees when it pulls down on you, which is kind of, there's no real big reason why that needs to be the case, but it is the case. Anyway, you guys get that? Does that thought experiment make sense? Yeah. And then we've already talked about the astronaut in orbit, right? That's a big one. Okay, why does there's an astronaut, Mr. or Mrs., whatever, astronaut out and orbiting in the ISS, International Space Station. They feel weightless. Why do they feel weightless? They're in free fall. The wrong answer to that, a lot of people will say, because there's gravity in space. Wrong, right? That's wrong because, how does the moon stay orbiting the Earth? Gravity. What keeps, there's obviously gravity in space. Otherwise, we wouldn't be here. There wouldn't be any stars or planets or solar systems or galaxies or anything. So what's happening on an orbit is, here's the International Space Station. It's actually perpetually falling. And so if you're inside of that, you're falling too. So the whole time, you're just falling with it. And so there's an mg vector, but the floor is not pushing back on you because the whole system, the whole box is falling. So he travels this way and he falls. He travels this way, he falls. He travels this way, he falls. But it happens smoothly, so you just travel in this orbit. Oakley dokley? Oakley kadokely? You sure?
Well, I was actually reading that technically the space station is truly falling a little bit because it's slowly deorbitizing.
We gotta put that back.
Yeah, so any orbit, whenever you orbit something, here's something. Yeah, you can orbit a perfectly stable orbit, which means you can theoretically orbit forever, or you can have an orbit that's decaying. I think that's what you're talking about. Yeah. You can decay inward and crash, or you can be spiraling outward if you're going a little bit too fast, right? Yeah. So,
because they're just saying they're have to disassemble it or move it or whatever at some point.
If you want to read something really scary, read about all the space debris out there.
Yeah,
there's all this stuff out orbiting the Earth, stuff like old satellites, and all it would take would be they say all it would take would be one major collision between a satellite and an old decommissioned satellite, and boom, that would smash into a million pieces, and then it could cause a chain reaction, knocking out all the GPS satellites and all that stuff. So that's pretty neato. What? I don't think it could be visible to the naked eye, but it could be. What if you zoomed in? Maybe, I don't know. Anyway.
Oh yeah, because it's that easy.
There's a great podcast I listened to once where it was this guy talking about how he's part of this commission that kind of monitors that space and tries to look out for collisions, and they're kind of interviewing him. He's like, well, yeah, my staff is 6 people. They're well, if you saw there was going to be a collision, could you stop it? And he's like, not really. Okay, so anyway, back to the problem. So what's happening here is that the net force would be this minus this. So I could be in an elevator traveling upward at constant speed, right? If you're traveling at constant speed, then what's your net force? 0, right? Constant velocity means no acceleration, which means the net force is 0, which means these vectors are the same size. So if you're traveling, if you've ever been in a long elevator ride, once it gets up to speed, you feel more or less normal. The only difference is maybe the floor is moving ever so slightly, so you have that kind of sensation of moving, but you're on a really nice elevator, you wouldn't be able to really tell the difference between moving upward at constant speed and just standing on ground. Okay. 35. So everyone understands why this means you feel heavier? If this vector is bigger than it is right now, I'm standing here right now, my vector would be that big. If that vector is bigger, you feel heavier. If that vector is smaller, you feel light. So on 35, if you are at rest and start accelerating downward, so here's me. Let's say the acceleration vector points down. Well, here's my mg again, my force from gravity. So what if my net force points this way? So this is also F net, or the direction at least. What does that mean for this vector?
Smaller.
It must be smaller. So my normal force that I feel on my feet, I go, wait a second, that normal force that I'm used to feeling on my feet is a lot smaller than it used to be, or it typically is, so I feel light. I feel less. Exactly, yeah, the ground is trying to get away from your feet. Now here's the thing, if you make this acceleration 9.8, then you'd feel weightless. If you make this acceleration like 20, you could smash your head on the top of the ceiling. Hello. It's called classroom. Yeah, like he's 2-2. What room is Mr. Osborne? Is it 221? No, it's Mr. Bill.
This side.
There you go.
Thanks, so she didn't tell you what number it is. It's
221.
221. No worries. See ya. Okay. Okay. Cool beans. Constant speed. So if you're traveling at constant speed, then you're like we talked about a few moments ago, your net force is 0, and so you feel the same. You don't feel lighter or heavier. And then 37 and 38. So if you're traveling upward, this is going to cover every possible permutation, I guess. So here, this is another interesting one. I don't know. The more you think about this, you guys know how fast we're going, like right now? Like super fast. I don't know the number, but thousands of miles per hour traveling through space. But we're traveling more or less at a constant speed through space, more or less. I mean, technically, we're not traveling in a perfectly straight line, but we're not speeding up or slowing down right now. So we don't feel any sort of sensation, but that's what happens if you're in an elevator. Even if you're traveling up like really fast, say my velocity points up, well, if my acceleration is 0, then these two vectors are the same, right? And so there's a fancy name for that called an inertial reference frame. Where you're just traveling at a constant speed. And so what that says is if you're traveling at a constant speed, you can't really tell the difference. From your frame of reference, you can't tell the difference between traveling at 100 miles per hour and traveling at 0 miles per hour. There's no difference to you. You can't tell. Here's another, that's a big one. Einstein ran with that idea. He took that idea and combined it with the fact that, you guys ever heard of this one? Like, we're not going to talk about relativity in this class, but it's kind of fun to just mention. If you're in a car and the car's traveling, say, 100 miles per hour, and then you stand up there and you throw a ball at, like, say you can throw a ball at 50 miles per hour, how fast will the ball be going from the perspective of someone standing on the side of the road? 150, right? That's called like Galilean edition. Galileo, like the dude was at Italy. Anyway, Galileo. We all know who Galileo is roughly. Huh?
I don't know if I do that. The ball's just in the top of the car.
Okay, let's say it's going 10. Does that make you feel better? 10. Now the ball's going 60, but you get the idea. You can add up velocities, okay? Or if you're on a cruise ship, and the cruise ship's going 30 miles per hour, and then you can run 5 miles per hour, okay, they add up. But then Einstein talks about, this is a big thing in science for the last 100 years. What if I turn the headlights on? That's a headlight, I think. Okay. How fast does light go? It goes the speed of light. It goes, it's 300 million meters per second. But would it be going 300 million meters per second plus 10 miles per hour? Would it be going faster? The answer is no. That was a big question for a long time of like, would it be going faster or no? Big open question in physics until these two TikTok savages proved, Michelson and Morley, I think their names were, they kind of proved it with this experiment. Anyway, so once they had established pretty conclusively that no, it doesn't matter if it would not be the speed of light plus 10 miles per hour, that basically the speed of light is the same no matter how fast you're moving. So Einstein took that and ran with it and came up with all these crazy results about like time dilation. You guys have seen Interstellar, right?
Actually, yes.
Is Interstellar
Prove.
that like it's not going faster?
So they did this experiment involving bouncing like I'm trying to remember if it was lasers or just light. I think it was lasers. Now I'm like, they did it in like 1890s, so they don't have lasers. It's called the Michelson-Morley experiment. And what they did was they had this apparatus. This is gonna be a poor explanation, but the general idea is Earth is traveling through space, right? So say Earth is going this way at this moment, who knows? So Earth's traveling this way. And they took this light, there's like a mirror in here, and they bounced it off, they set it on this path where they're able to measure how long it takes for the light to traverse this sort of this pattern. The difference is tiny, very tiny. I actually did this experiment in college once, part of a class. It was like, you had these instruments. We have obviously more advanced instruments now, but you measure how long does it take the light beam to go bounce, 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 whatever the path is. And then because the Earth is moving, if the speed of your reference frame mattered, then you have like different times based on like what path you took. So the simplest example is like, simplify it and say, say the Earth, here's the Earth. Say the Earth's moving this way right now. And you have like two mirrors. Well, it would take longer for the light beam to travel this way than it would to travel this way if the Earth is moving this way. Right? Does that make sense?
Because the Earth is moving here.
Yes.
So I feel like we should just measure light with like the police speed scanners. I feel like those could get you like a millionth of a mile an hour over.
Those work on the Doppler effect, I think. We'll talk about that later this year. But anyway, what was I talking about? Anyway, you guys haven't seen Interstellar?
Is it that movie
No,
where
I
like
see
they go
that.
like in the big black hole?
Yeah.
Yeah, I've seen
And
it.
they have like they actually create artificial gravity. There's some sort of force that keeps them.
Oh, that's easy peasy. You can do artificial gravity is easy. You just put people in a cylinder and then spin the cylinder. You guys have experienced that. Have you ever did that ride that spins you around? That's literally all they do. In that movie, they've done it in 2001: A Space Odyssey. You put,
Where they put them on the.
we'll talk about this in this class too. You basically put people in a centrifuge and spin them around. And we'll actually do the calculation of like, if you tell me how big the tube has to be, so say it's a 10-meter radius tube, how fast do you have to spin this around so that everyone inside feels like they're just chilling?
In 2001: A Space Odyssey, didn't they have like a big hamster wheel? Big guys.
Yeah, there's a famous scene where he jogs around. They do a tracking shot. They show him walking, running around this, and that's the idea. This idea has been around for a really long time that you can spin this around. Now in space, it works great because there's no gravity. Assuming you're far enough away that you're not in a strong gravitational field, you would not know the difference. But anyway, in that movie, I'm so off topic here, but Einstein ran with this idea of inertial reference frame and the fact that the speed of light doesn't depend on how fast you're moving when you measure it, and came up with all these crazy ideas like time dilation. Like if you're traveling really fast, time slows down for you. In Interstellar, it's also if you're in a really strong gravitational field, time slows down. So they go, it's like one of the greatest scenes of all time. They go down to this planet. I'm so triggered that you guys haven't seen this movie.
It's really good.
It's like one of the best movies ever made, I think. They go down, there's this black hole, right? And there's a planet orbiting the black hole. There's spaceships out here. Spaceship. This dude, he has to stay on there and wait. And he's like, okay, because every hour, 1 hour on the planet is like 7 years on the ship. And so this dude is like, I'll stay here and try to like do these equations, try to figure out how gravity works. And they go, okay, they go down there, and so by the time they get back, this dude's been just chilling up there waiting for them for like 20 years. And he's all got gray hair and stuff.
But they were only there for a couple hours.
Yeah, they're only there. Yeah, so that's time dilation. In the strong gravitational field of the black hole, that's definitely possible. Same thing where if you could get in there's a really good science fiction novel about how they like get into these soldiers. It's called The Forever War. They get into these spaceships and they have to travel really far distances, but they travel at like 99% light speed. So by the time they get to the war zone, it's like 500 years later, and the aliens have different technology than the last time they were there. So it's a pretty interesting book. It's all supposed to be like I think it's supposed to be some sort of allegory for the Vietnam War. Okay. What?
Like when the sun dies, you won't actually know for like a while.
I think it's like
I mean, humanity will have been wiped off the face of the planet long before that.
So once you like also done, you won't even know.
The sun will have already expanded and engulfed the Earth before it dies.
Yeah, but like that's the origin, and then like when it starts to go, like we won't see that it goes until after it's like.
I know what you're talking about. If you just magically, like Snape kills Dumbledore, the planet, the sun, you went boom, magically gone. It would take like 8 minutes, roughly. I think it's 8 minutes for you'd be like, oh, sun's looking cool over there, and boom, 8 minutes later. 'Cause it takes the light 8 minutes to travel. I think it's 8. Okay. Anyway, let's finish this problem here. Sorry for being off topic. I didn't mean to. Watch Interstellar, guys. It's great. Christopher Nolan is like today's Stanley Kubrick. I mean, you gotta respect the genius. Inception?
Not really.
Do you guys not watch movies?
Not really. I do.
Watch
Watched
that.
Halloween last night.
Huh?
Watched Trees Halloween.
Did you watch?
Trees Halloween. It's on Netflix. It's like number 2 in the world for the US right
Okay. So okay, we'll finish these 37 and 38.
What's this?
Okay. So if you're this is as a kid, we'd always jump at the top as the elevator reached its final floor. If it was traveling upward, we jump at the top and try to get some extra Michael Jordan air. So if you're traveling upward and slowing down, that means your acceleration is what direction? You're slowing down. It's down. Same with your F net. So your net force must point down in this scenario. That's the first key to understanding it. So if you're traveling upward, slowing down, your net force must point down, which means this must be happening. And then you might go, wait a second, Isn't that the kind of the same scenario as number 35? And the answer is, yeah, 35 is the same thing. Your net force points down, you'd feel lighter. So you'd feel light. All right. So 38 would be you're traveling down. This is our fun one. As a kid, I don't know, just feeling heavier would just be neat. You're traveling down, so if you're traveling this way and you're slowing down, a good rule of thumb is this phrase slowing down means that your acceleration vector points in the opposite direction as your velocity vector. Does that make sense?
Yeah.
So in this case, my net force has to point upward, which means I'm going to feel heavier. My normal force is greater than it usually is, so I would feel heavy. Heavy. So, take a shot at these numerical problems, the ones where you actually try to calculate. They're pretty straightforward. The scale reading is just this. That's all a scale does. It's nothing magic. It tells you how much force is exerting upward to keep you doing whatever you're doing. So try a couple of those numerical scale problems. And tomorrow we'll start going over the block, yes.
So on a scale, find your like mass, really you just have to divide by gravity, like divide by 9.8.
Sort of. So an American scale is typically going to tell you pounds. So let's say I step on a scale and it says I'm like 170 pounds. What I would do is first, because there's 2.2 pounds for every kilogram in terms of weight. So I'd first divide by 2.2. And that would tell me how many, but the thing is that conversion, that 2.2 number is a pounds to kilograms conversion. So does that make sense? You'd only divide by 9.8 if somehow the scale is reading out in newtons. But like in this problem, like on number, in one of the problems I give you, we live in a bizarro universe where like Albert on 39, his scale is calibrated to read off in newtons. So yes, he would divide by 9.8 to figure out how many kilograms he is. So, how many kilograms am I? Let's see. 77, roughly. Feels good. Feels good. So you are your one